Yeah, so I don't remember whether Dr. Converse had you like proving some of these kind of things from the vector space axioms in that first couple of weeks, but that would be something that I think would be worth being able to do. So the idea here is to try to prove this property. Do you see the difference between the left side and the right side? This is just taking v and scalar multiplying it by -1. This is actually not a -1. This is a symbol for the additive inverse of v. So remember, one of your axioms of a vector space is that you can add a vector to its additive inverse. And what is that supposed to give you? 0. Exactly. So that's one of the axioms, right? So let's think about how we could prove that. We're trying to prove that the guy on the left is the additive inverse of v. Well, how do I prove that something is the additive inverse of v? I want to show that two things are additive inverses of each other. If I want to show that 7 and -7 are additive inverses of each other, how would I convince you of that? Add them together and see if I get 0, right? That's exactly what I have to do here too, right? So my proof would be my proposed additive inverse, which is -1 times v, right? I'm going to add that to v, and I'm going to see a few steps later. Please do not write, do not write the conclusion here. We're not there yet, right? We have to prove it. Put your 0 down at the bottom, right? That's what we're going for, but don't. Some people tend to write it right away at the beginning, and then it's confusing. So keep that 0 down at the bottom, okay? So let's see if we can fill in the steps. Let's see if we can do this. Does anybody have a suggestion, maybe what I can do for the first step here? Remember, you have basically up to 8 vector space axioms. Pardon me? Pull out a v. So factor it out. I'm going to do one other thing before I do that. Okay? Because I have a scalar in front of this v, but I don't have a scalar in front of this v. But I can put a scalar in front of that v by just simply putting a 1 times v there. Remember, we have that unit property. And again, somebody was asking me earlier about memorizing the different axioms. You don't have to, remember that this is, VS5 or anything like that. Okay? You can just say by vector space axiom. So by vector space axiom, don't worry about the number of it. Actually, all of these steps are going to be vector space axioms. So now I can pull out the v. I'm actually using, I'm using the last axiom, aren't I? So my v with 2 scalars added together. So this is going to give me -1 plus 1 applied to v. Okay, and now what can I do with that?
Add -1 and 1.
Right, -1 and 1, those are just numbers, right? So I can pull that out. That's 0 times v. And so this is also a vector space axiom. This is also a vector. This is just addition. This is just -1 plus 1. -1 plus 1 equals 0. That's not even an axiom, really. Okay. This last step, 0 times v equals 0, I believe I actually proved that in the class. Like on the very first day I came in here. I hope I'm remembering that right. It's not an axiom. This is not an axiom, but it's another one of those things that you can actually prove from the axioms, right? So this is, I'm just going to say, you can actually do this as well, guys. You can say result from class. Just make sure it really was a result from class. Not something made up. You guys can really play games with me. You say, yeah, Dr. Converse went over all of that stuff. I'm like, I'm going to have to take these exams over to her house and have her verify all this stuff. But yeah, so that is a result from that. Is anybody finding it?
I don't remember that.
We're not finding it? Okay, maybe I should explain it then. Actually, I thought I did, but you know what? Oh, you know what? I did not do that. I did not do it. I don't know if you guys know how many classes I'm teaching right now, but it's an insane number of classes with like overlapping material from different classes. I know that I explained that, but it wasn't with you guys. Okay, so I probably wouldn't do this question if it involved two parts like this. Let me come over here and explain the asterisk. So I claim that 0 times v is 0. Now, we have to be very clear that this 0 on the left is the number 0. This 0 on the right is the vector 0. When I teach the lower division linear algebra classes, I always put arrows on all of my vectors to keep them straight, and it's perfectly fine if you guys want to do that. The reason I don't do it now is just because the book doesn't do it, and they kind of expect you to just know that, okay, if I'm doing a scalar multiplication of 0 with a vector, this has to be a vector. Okay? So this 0 is a vector, this 0 is a scalar. We're trying to prove that this 0 times v is just the 0 vector. Okay, so this is a little mini proof that finishes the main thing we were proving over here. By the way, is everybody good that what's on this left board proves that box? Okay, you've added these two things together and gotten 0. So that means that the additive inverse of this guy is this guy. Right? That's what you needed to show. But there's this one little loose end right here that really technically needs to be shown as well. The trick to doing this is to just do the following. You just start with the 0 times v on the left side. Have you guys, do you know how to, maybe I should see if anybody knows how to do this. Yeah.
Are you supposed to do v1 to the vn and multiply it in?
No, we don't need to create any more notation. We just have the v is the only vector we really need to work with here. 0 plus 0. Yeah, exactly. Oscar's got it. You just take 0 and write it as 0 plus 0, and then you split it apart using your vector space axioms. So 0 plus v times 0 plus v. Great. So we have that. Now what do we do? So the left side I've got 0 times v. The right side I've got 0 times v plus 0 times v. Okay, subtract. Let me just be really correct about it and say that we're going to add the additive inverse of 0 times v. Every vector has an additive inverse. So the additive inverse is the negative of 0 times v to both sides. So on the left, we got negative of 0 times v added to 0 times v. On the right, we have negative of 0 times v added to, well, we have 0 times v plus 0 times v. So I'm just being very careful with every single step here. And what does that give me now on the left side? Right, you're adding a vector to its own additive inverse, so that's just 0, right? And then what am I going to do on the right side? So cancel is basically what we want to do, but how could I do it like more properly with my axioms? Say again, Robert? Right, I got to regroup the parentheses. That's right. I got to move the parentheses around, so I'm going to put the negative 0 times v plus 0 times v here, and then plus another 0 times v. So you're moving the parentheses from the second and third terms back to the first and second terms. And now this is just the additive inverse of a vector added to itself. That's just going to give you 0 again, right? So we get 0 is equal to 0 plus v, but the 0 vector, when you add it to anything else, just gives you 0 times v. So there you go. That's how you would prove that, because you've got a 0 here. I'll just recopy it there. 0 is equal to 0 times v. There's several different axioms I'm using here. There's the associative axiom. There's the 0 vector property. There's the additive inverse of a vector added to itself, adds up to 0. So I won't write it all out exactly which axiom I used where, but that's all I was doing there. What do you guys think? Does it make some sense? Pretty reasonable? Okay, great. So that's about all I'm going to practice on with the vector space axioms. We've got a couple examples here. I could propose a structure to you and then ask you to see if you think it works. Those kinds of questions are always good. So okay, let me move on to some other things. What happened to my?
Oh, it's up there?
Oh, that's what I'm looking for. Yeah, I was like, where did my questions go? Okay, let's do a new problem. Okay, step back over here. Obviously, I could ask you, a bunch of standard calculation problems. Find a coordinate vector of such and such relative to a basis. Find a matrix representation of some transformation relative to beta and gamma. Right? Those kinds of very computational things are just very similar to what you just did in the last couple of homeworks. So, some of those computational things, I may not go over a lot of those today, just because I think that that's probably just a little more of the most routine kind of stuff. I want to really make sure that you've got some practice on these slightly more abstract problems. So let's try this one. Okay. So given a matrix A, which is, let's say it's n by n. So this would be mn of R, right? Let TR of A be the trace of that matrix. So that's just the sum of the main diagonal. And what I want to do here is prove that if I make the set S, which is going to be the set of A, an element of Mn of R, such that the trace of A is equal to 0, let's prove that that is a subspace of Mn of R. Okay. So this is my proposed subspace right here. It's those matrices that have a trace of 0. It's those matrices that have a trace of 0. Okay? Everybody good so far? What do I have to do? Closure under addition and scalar multiplication. Exactly. It's always those two steps. Okay? So let's see if we can do that. It would be really helpful if I do ask a question like this, if you could separate those two parts clearly for me. So closure under addition, I like to just write the CL plus like that. Okay? So closure under addition. The way that we do that is we take two vectors that are in S. Okay? So in the case where the vectors are matrices, I might use capital letters for that. So I would just start off this way. Let A and B be elements of S. Okay, and then what that means is that, well, the trace of A is 0 and the trace of B is 0. Right? So in other words, we know that A11 plus A22 plus ... plus ANN is equal to 0. And B11 plus B22 plus ... plus BNN, all of those add up to 0. Okay? So this is the trace of the first matrix, the trace of the second matrix. Okay? So then I want to look at A plus B and figure out its trace, right? So what we would like is the trace of A plus B, hopefully it equals to 0. Okay? So why don't you guys see, while I'm erasing this board, see if you can fill in the next step there. Trace of A plus B. So we're going to add at the main diagonal of A plus B. What's the first main diagonal entry of A plus B?
A11 plus B.
A11 plus B11, right? That's the upper left corner of the matrix. Okay, and then the next entry would be?
A22 plus B22.
Right, so A22 plus B22, and we just go like that, dot, dot, dot. If you prefer, you can express these as summations. You use the summation notation, but this is fine, just to write it like this. These are finite sums anyway, so it's not like there's any issues of convergence or anything of the series. So we just add up those numbers. And then what would you suggest that I do next? Please don't just write equals 0 now. I mean, you could, and then nobody could really argue with you, because you're right, it does equal 0, but then you're skipping the main step. The main step is to show that, okay, we have to regroup these terms to get the A's together and the B's together. So sometimes people are a little sketchy, and then I have to sort of, you don't want to make me have to like read your mind and say, oh, I think Jasmine knew this is what she meant to say, but I have to kind of sort of imagine that's what she was thinking. I'd rather just, if you just write it down for me, then I don't have to wonder if you really understand it, right? So let's just break it up like this. Up to B and N, and now we have 0 plus 0. Okay, I'm going to do something wrong. Okay. I'm gonna make a mistake, and I want somebody to tell me what I'm about to do wrong. So equals 0 plus 0 equals 0 element of S. What did I do wrong? If I read this out loud, it starts at the beginning over here, right? This is where my chain of equal signs begins. The trace of A plus B equals, and then is an element of S. Is the trace of A plus B an element of S? No. No, the trace of A plus B is a number. I see this so often, people will just throw that element of S thing at the end. It's not the trace of A plus B that is in S. Instead, what we want to do here is we want to say, thus, A plus B is an element of S, and put a check. Okay, so this is a better way to go. You do need to say this, though. If you don't say this line right here, that's kind of missing the punchline. So be sure to include that punchline at the end. Okay, is everybody comfortable with this part of the write-up here? Okay, just slow me down if there's any questions as we go along. It's nice to be able to take our time today and just go through things carefully. Closure under scalar multiplication, the way I always like to set that up is I like to just say, let capital A be as above. So you just take one of the two vectors from the first part, and then we have to grab a scalar. I think the book usually uses C for the scalar, so I'll just do that. It's from the field. And what we're going to examine now is C times A. Okay? So then I want to look at the trace of C times A. And again, it's tempting to literally just pull the C right out, very first step, factor the C out. But I think it's, again, better to actually imagine, well, what are the entries of this matrix, right? The entries of this matrix are C times Aij. So this trace would be, CA11 plus CA22 plus dot, 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 plus CANN. Try not to just factor the C out blindly at the beginning. Like, show the steps that you have there. All right, so that becomes, now I can factor out the C. I think everybody can see how we do this here. I can factor out the C, and we get C times 0, which is just 0, of course. So C times A is an element of S. Great. So this is a subspace. That make sense? Okay. If it's a subspace, then I'm going to ask a follow-up question. Oh, I should mention one other thing. If I had phrased the question differently here, if I had said, is S a subspace? Would you have done anything differently?
Yes.
What would you have done
It says
differently?
yes at the end and circle it.
Well, you'd have to make sure you answer the question, yes or no, right?
Make sure, what you start with is a vector space.
Well, I know that Mn of R is a vector space. So for a subset of that to be a subspace, really just means it's a vector space. That's really what this question is asking, is S itself a vector space? So if, instead of asking you to prove it straight off the top, if I had said, is this a subspace, yes or no, would you have just launched into verifying the closure of addition and scalar multiplication, or would you have wanted to assure yourself first that this, before you write it all up and find out it doesn't work, is there something that you can do, like right off the top, when somebody gives you a proposed subspace and you're not sure, is there something that you can do right off the bat to kind of sort of at least give yourself some assurance that it's going to work at all?
Isn't there a theorem about the zero vector being the same?
That's it, the zero vector. That's what I wanted to mention. If the zero vector is not part of your set, right, then you definitely do not have a subspace, and you can circle no and just say that, fails the zero vector check or whatever, and then you're done, right? Because how you proceed when something is a subspace versus when it's not a subspace are very different, right? If something's not a subspace, well, you just have to you're not going to start writing any of this up. You're going to either talk about the zero vector not being there, or you're going to give me an example to show that something fails in this in these two steps, right? So if it's a yes/no question, I would recommend before you launch into it, at least just check that zero vector. Now, obviously, the zero matrix, we all know this, that the trace of the n by n zero matrix, 0 sub n is my n by n zero matrix, of course is just 0. Now, the other thing to keep in mind, guys, is just because the zero vector is in the set, that does not mean that it is definitely a subspace. It just means that at least you have a chance that it might be a subspace. So if the zero vector is missing from the set, it's game over right away, right? That it's definitely not going to be a subspace. And you could just cite that. Okay. Anyway, so I just wanted to remind you about the zero vector. That's like, the reason that I like to do that is it's just so easy to check it. I know what my zero vector is. I just check, does it satisfy the condition? And in this case, it wouldn't have gotten us anywhere because we would have said, yep, the zero vector is in the set, so then you're still stuck doing all this work. But at least for a yes/no question, we recommend. Like if I threw a question like that at you on the test, that would be one that I would hope, like where the zero vector was missing, I would want you to see that right away and say, no, there's no zero vector, and move on, right? That should not be something that takes 10 minutes. Okay, let me ask a follow-up here. So for n equal to 3 in this problem above, give a basis for S. Let's try to write down a basis for S.
Are we done with the proof here?
Yeah, we're pretty much done with the proof. We checked closure under addition. We checked closure under scalar multiplication. I suppose one sentence at the end.
The element of 0?
Pardon?
The existence of the element of 0 there?
Well, yeah, that's kind of what I just did right here.
That's enough?
Remember, I think it was this class that I said it. I think I told you that if you verify closure under addition and scalar multiplication, then as long as your set is non-empty, which this is definitely non-empty, there are definitely matrices that are traceless. In that case, it's definitely, the zero vector is definitely already covered by these two axioms. Why is that? Well, because you can take any non-zero vector, we actually just did this, you take any non-zero vector, you can scalar multiply it by 0, and what we proved is that, well, that is equal to 0. So if closure under scalar multiplication holds, then by taking any non-zero, any vector at all, actually, in the set, you can multiply it by the scalar 0, and because this is closed, this guy will be in S. So you're actually getting, as an extra bonus from doing this closure under addition and scalar multiplication, you're getting an extra bonus of having the zero vector checked for you at that point. So you don't really need to check it explicitly. But I like to check it, again, because it might not be in the set at the beginning, and then I can rule the thing out right at the beginning. Am I making any sense? Okay. Has anybody got this figured out? How are we going to find a basis? This is for the 3 by 3 matrices that have a trace of 0. How am I going to get a basis for it?
You can write a matrix that has 0
So I might try to write the form of, I'm going to try to write the form of the vectors. Guys, that's actually how you want to do these problems. Okay? You want to write the form of the vectors that are in S. Okay? So a typical, here's the solution, a typical vector in S has the form, okay, so let me call it capital A. Robert, can you help me with the form here? It's a 3 by 3.
The elements and everywhere except for the diagonal. So the diagonal just has 0.
Like this?
Yeah. And then every other element got like A,
Just
B.
the whole alphabet?
Yeah.
Like that?
Yeah.
Okay. Does everybody have their erasers handy? So here's the thing. When you're putting down the form of the vector in your set, it has to be the most general form. Do you have a suggestion what I need to do differently?
Yeah, so for the last one, diagonal, would you write, so for the first diagonal, you're going to put like A11, the second one would be A22, the last one would be minus A11 plus A22.
Okay, the diagonal does not have to be all zeros, right? It just has to add up to 0. So that means I can have, I'm going to use totally different letters just to kind of make it more obvious. I can actually put any two numbers I want right there and there. And then, as Jennifer's saying, the last slot has to cancel that out. So my main diagonal in the most general form would look like that. Okay? So this would be the general form. And now I can do what? To get
Bust out.
Thank you. Bust out the variables, right? We're going to bust out, how many variables do I have? Oh boy, I have a lot of variables. So I have an x that's multiplied by, actually, you know what I'm going to do? I am going to use my e notation. Remember my eij notation? So the x is multiplied by an e11, but also a minus e33. Right? And then let's just do the y variable next just to get it finished with. So for the y variable, that's multiplied by the e22 minus the e33. Okay, so that takes care of the main diagonal portion. And now I have to do, plus a times e12 plus b times e13 plus d times e21 plus c times e23 plus e times e31 plus f times e32. It's a little bit of a long thing to write it out, but that's kind of what you would expect to have. Okay? Yeah, good. Did it just stop? Oh, and I'm not supposed to be writing over there.
Yeah.
Oh, I forgot about that. Okay, I'm supposed to come back over here.
Oh, we have 1 minute left. We can move this.
Is it still on?
Yeah.
Oh, well then I'm just going to turn the camera.
No, yeah.
Yeah, sorry guys, you can't see that if I do that. There we go. So that's what I was just writing down. This is breaking down my matrix A into these terms like this. Okay? So then how do I get my basis? Say again? So the variables have been busted out.
Oh,
Is this my basis?
don't you have a solution and you want to in common?
We have to make a set, right? We have to actually write the set down that has all of these vectors in it. So we would have, e11 minus e33, and then e22 minus e33. Okay, and then we would have e12, e13, e21, e23, e31, and e3.